So, as we discussed in the previous sections, that the total time response consists of transient part and steady state part. All the time domain specifications in the transient part we have discussed, and few problems also we have solved on that. Now, there is one parameter that will appear in the steady state part of the response. So, this is called as steady state error. This is represented by ESS, steady state error, and according to final value theorem, limit t tending to infinity E of t, a function in time domain, is equal to limit s tending to 0 s E of s, according to final value theorem. So, the steady state error E of t as time tending to infinity is the steady state error. That is the definition of steady state error. Error function or the response as time tending to infinity means the transient part of the response must die. The remaining part of the time response is called steady state response. That response in the steady state, if it is differing from the input, then what is the error? For example, you are familiar with this diagram. Say R of s is the input and the function system is described by g of s, and this is the output C of s. Assume unity feedback control system, then this output of this error detector is E of s. So, what is meant by E of s? E of s is the error signal. So, what is the deviation? What is the deviation from input to actual output? So, we say that E of s is equal to R of s minus C of s. So, if there is no error, then these two are equal, desired output and actual output. If both are same, error is 0. So, the error is the difference between desired and actual. So, you can see this R of s is as it is, and this C of s can be written as E of s multiplied by G of s. Now, this is E of s, error signal of this error detector. Bring this E of s this side. So, E of s into 1 plus G of s is equal to R of s. Now, the error signal E of s is equal to R of s by 1 plus G of s. This you substitute in this function. To get the steady state error, ESS is limit s tending to 0 s into E of s is given by this R of s by 1 plus G of s. So, this is the expression for steady state error. Steady state error, it depends on nature of the input. So, R of s we consider as input. So, steady state error depends on input, the nature of the input. So, let us see now, if input is unit step. If the input is unit step, let us substitute here. So, ESS is equal to limit s tending to 0 s into R of s is replaced by 1 by s by 1 plus G of s. So, we can write this as 1 by 1 plus limit s tending to 0 G of s. So, the given G of s, limit s tends to 0, this part you can call as Kp. Kp is a constant. When you substitute s equal to 0 in G of s, you will get Kp, where Kp is known as position error constant. Position error constant. So, this Kp is given by limit s tending to 0 g of s. How to get Kp is limit s tending to 0 in the given function g of s, you get this constant, and 1 by 1 plus Kp is the steady state error for unit step input. So, as the expression for the steady state error is limit s tending to 0 s into r of s by 1 plus g of s. So, steady state error depends on the nature of the input. Now, if the input, the second case r of s is equal to 1 by s square, means unit ramp input, then the steady state error can be written, substitute r of s by this. So, you get limit s tending to 0 1 by s plus s into g of s. So, s is very small, s is very small when compared to this part. So, we can write this as limit s tending to 0 s into g of s. So, this can be written as 1 by kV, where kV is velocity error constant. kV is known as velocity error constant, and steady state error for ramp input is given by 1 by kV, where kV is the constant, velocity error constant. How to get this? By substituting s equal to 0 in g of s. So, limit s tends to 0, s times g of s is the kV velocity error constant. People will be misunderstanding that velocity error means error in velocity, but it is not so. In the previous section, we have seen when the input is unit step, you have got a position error constant. It is called position error constant, and this is velocity error constant. Position means it may be an angular position, or in the case of temperature control system, this position is treated as temperature. In the temperature control system, temperature is related to position. So, change in temperature is change in position, because unit step input is nothing but sudden change. So, position error means the error in the position, and that position may be temperature or pressure or angular displacement. Now, velocity error means, for example, if I say position is temperature, then velocity means it is not error in the velocity in temperature control system, but this velocity is known as dt by dt. Change in temperature is nothing but velocity, because in temperature control system, position is treated as temperature, then rate of change of temperature is nothing but velocity. Similarly, when I have the error in the d square t by dt square, if it occurs in the temperature control system, then I will write here as a acceleration error constant. So, it is not error in the acceleration, but it is d square temperature by dt square. So, the third case, let us consider input is r of s unit parabolic. This is the input. Here this is a unit ramp input and this is unit parabolic input. Now, if you calculate the steady state error for this, again you get limit s tending to 0 s into 1 by s cube by 1 plus gs. So, this can be 1 by s square plus s square g of s, limit s tending to 0. So, you can ignore this term because it is very small when compared to this, and this can be written now as 1 by limit s tending to 0 s square g of s. This is nothing but 1 by Ka. Ka means acceleration error constant. Ka is acceleration error constant. So, you can see now we could get 3 constants. So, the 3 error constants we could derive Kp, Kv and Ka. This is limit s tending to 0 g of s. This is limit s tending to 0 s into g of s. This is limit s tending to 0 s square g of s. You can observe the change. There is no s here, there is an s, there is s square. All 3 error constants, and the steady state error is equal to 1 by 1 plus Kp if input is unit step. If input is unit step, steady state error to be calculated using this formula where Kp is equal to limit s tending to 0 g of s. If the question is calculate the steady state error for unit ramp input, then you should use the formula 1 by Kv for steady state error, where Kv is limit s tending to 0, this function. And if the question is calculate the steady state error for unit parabolic input, then you should use the formula 1 by Ka, where Ka is given by this. So, these are the 3 error constants which will give the magnitude of steady state error for various inputs. So, we have seen in the previous section that the steady state error depends on nature of input. Now, let us see that steady state error depends not only on the nature of input, but also it depends on type number. So, what is the relation between steady state error and type number of the system? So, g of s, the system transfer function, is generally represented by k into s plus z1, s plus z2, so on, zeros, and s plus p1, s plus p2, etc., and you have s power n also. So, what is the significance of this n here? S power n indicates the number of poles. N indicates the number of poles at origin. Number of poles at origin. Or we can say that number of integrations involved. Number of integrations involved in the system. So, if n is 0, we say that it is a type 0 system. If n is equal to 1, then we say it is a type 1 system, and so on, and so on. Now, what is the effect of this type number on steady state error? Very important to see. So, now let us consider the input as we discussed in the previous section. If input R of s is 1 by s. So, for this the steady state error is to be calculated using the formula ESS is equal to 1 by 1 plus Kp, position error constant. This Kp is given by limit s tending to 0 g of s. Limit s tending to 0 g of s. So, if you see that this g of s is given by this function generally, then if you substitute s equal to 0 in this function, assume that it is a type 0 system. So, what is the meaning of type 0 system? That n equal to 0 here means there are no poles at origin. N is equal to 0 means no poles at origin. Then if you substitute s equal to 0 in this function, then what happens to g of s? What happens to g of s? This is s power 0, 1. So, s 0, 0, 0, then you will get k into z1, z2 by p1, p2, etc. So, it is a constant. g of s will be constant. That constant, if you substitute here in the Kp, this steady state error will have some constant. So, we say that steady state error is constant if it is a type 0 system excited by unit step input. Now, let us increase the type number, say type 1. What does it mean? There is one pole at origin, n is equal to 1, type 1 system. Then if you calculate Kp for that, Kp is given by this function. So, what happens to the Kp? The Kp is given by limit s tending to 0 g of s, but there is one pole at origin here. So, limit s tending to 0 k constant originally. So, z1, z2 and all you have in the numerator, but there is one pole at origin s, and this 0 when you substitute here, the Kp value become infinite. Kp becomes infinity if it is a type 1 system. So, see the importance of introducing the pole at origin is Kp is constant in type 0 system. So, steady state error is constant, it exists. Error between the steady state input and output, that error is a constant for type 0 system. Now, when you got type 1 system, Kp has become infinite. So, the steady state error ESS equal to 1 by 1 plus Kp, that is infinity. So, the steady state error becomes 0. So, introducing the pole at origin makes the steady state error 0. That is the beauty of type number. Now, if you increase further, type 2 means there are two poles at origin. So, again if you calculate Kp, you will have infinite and the steady state error is 0. That means, beyond type 0, if it is type 1 system or type 2 system and type 3 and so on, there will not be any steady state error for unit step input. So, that is the significance of type number when input is unit step. Now, let us see that if input is ramp, then for what type of system the steady state error will become 0. Let us see that the input is unit ramp. Now, the type 0 system, again type 0 system. So, ESS is given by 1 by Kv, where Kv is limit s tending to 0 s times g of s. So, this is the formula for velocity error constant, used to be steady state error when input is unit ramp. So, if you substitute now s tending to 0 in the given function here, there is s in the numerator itself. So, if it is a type 0 system, there are no poles at origin, but if you substitute s equal to 0, there is an s here. So, definitely this function Kv becomes 0. So, for type 0 system, Kv is 0 if the input is unit ramp. So, steady state error is infinity. So, a unit ramp system for type 0, the steady state error is infinite, not at all advisable. Now, let us increase the type by 1, means there is one pole at origin now. So, if you calculate Kv for this, limit s tending to 0 s into the function g of s has one pole at origin now. So, in the denominator you have s. So, this s and s gets cancelled. So, you have a function in the numerator that becomes z1, z2 and so on, and in the denominator p1, p2 and so on. So, Kv is some constant you get for type 1 system. So, Kv 0 in type 0 system has become constant in type 1 system. So, Kv has been now introduced with type 1. So, the steady state error ESS equal to 1 by kV. So, it is a constant. Now, let us increase again by type 2. If there are 2 poles at origin, then again if you calculate the kV limit S tending to 0, S into the given function has now 2 poles at origin. So, you have S square term in the denominator. So, S gets cancelled. So, you have kV now infinity. So, this is a good thing that for type 2 system kV velocity error constant has become infinite. So, the steady state error becomes 0. So, for type 2 and above systems, the steady state error will become 0 when input is unit ramp. So, when the input is unit ramp, the steady state error is given by 1 by Ka, where Ka is the acceleration error constant, and that is given by limit S tending to 0 S square G of S. So, if you want to see the relation between type and steady state error, as in previous sections also, if it is a type 0 system, there is no pole at origin, meaning of that. So, if you calculate Ka for that, it will be 0 only, because there is S square in the numerator term. So, we can say that the steady state error is 1 by Ka, so it is infinite. Now, if type 1 system, if it is a type 1 system, then Ka is again, because there is only one pole at origin, so but there is a term S square in the numerator. So, again S appears in the numerator. So, Ka will be 0 even for type 1 system. So, the steady state error is infinite. If it is a type 2 system, means 2 poles at origin will cancel out this S square term. So, Ka will be now constant. So, the steady state error also will be constant because it is 1 by Ka. Now, beyond type 2, if it is type 3 system, then there will be S cube in the denominator, S square in the numerator. So, one S appears in the denominator. So, the Ka will be infinite and the steady state error will be 0. So, if it is unit parabolic input, then it must be type 3 system, means 3 poles should be there at origin to have steady state error 0. That way you can remember that 3 cases we have discussed. For unit step input, steady state error is 0 for type 1 and above systems, and for unit ramp and parabolic cases also we have seen. So, we can tabulate all these values at one place, so that you will know that steady state error is to be calculated for which type of the system, if input is unit step, unit ramp or unit parabolic. Let us tabulate all these error constants and steady state error for different types of systems. So, let us conclude now what actually we have discussed in the form of table, that steady state error depends on nature of the input and also the type number. Type number, as I said, number of poles at origin. So, if it is a 0 type, means no pole at origin, then there will be a steady state error for unit step input to be calculated by using this formula. Now, for unit ramp input, the steady state error is infinite. So, if the input is unit parabolic for type 0 system, again it is infinite. If it is type 1 system, then the steady state error becomes 0 for unit step, and here it is to be calculated for 1 by kV using the formula for unit ramp input, and this one again infinite. So, if the type is increased by 2, then steady state error will be 0 for unit step, even for this also 0, and this one will be 1 by Ka. So, you can observe that this diagonal means for type 0 system only you need to calculate the steady state error using this formula, where Kp is the position error constant that is given by limit s tending to 0 g of s. And if it is a unit ramp, you need not calculate for type 0 and type 2 and above systems. Only for type 1 system you need to calculate using the formula Kv limit s tending to 0 s into g of s. And for type 2 system you need to calculate Ka when input is unit parabolic using the formula limit s tending to 0 s square g of s. So, this is the way that error constants will be the indicative of how the steady state error exists for different types of inputs. So, if it is unit step input, we have written the formula 1 by 1 plus Kp. If it is not unit step, then the formula will be A by 1 plus Kp, where A is not 1, it is some value. So, it may be 10, it may be 20. So, it is not a unit step, but it is only a step. Similarly, if it is not unit ramp, then it is not 1 by Kv, but it is A by Kv. A has some magnitude. Similarly, if it is not unit parabolic, it is simply a parabolic function, then instead of 1 you will write A by Ka. This is the way you need to calculate the error constants. They are the figure of merits of the steady state error to be calculated.